So we've learned about paramagnetism and diamagnetism, okay, and we've seen why they happen, what is the reason behind paramagnetism and diamagnetism. Now we are going to look at another form of magnetism which is known as ferromagnetism, okay. You can think of it as your extreme form of your paramagnetism, okay. So magnetism, I'm making a spelling mistake over here. Okay, here we are. So this is, as I said, an extreme form of paramagnetism. Your ferromagnetic materials tend to get magnetized very strongly, okay. Your magnetization in a paramagnetic material is very feeble, okay. Your magnetization in a ferromagnetic material is very strong, okay. So the reason for this is your ferromagnetic materials, they have spontaneous magnetization, okay. Just like what we have learned in our ferroelectric materials, the same concept is what's present in your ferromagnetic materials. The only change is, instead of electric field you have your magnetic field, instead of polarization you have your magnetization, okay. So your ferromagnetic material also undergo what's known as hysteresis, okay. So if you're going to draw a curve between your H, which is your magnetic field, and M, which is your magnetization, it's gonna be something like a hysteresis loop, okay. So initially when you're going to start, your magnetization is going to increase like this. First it increases very fast, then it increases relatively slower, and it attains a saturation value, okay. Now if you're going to increase your magnetic field, there is not going to be any increase in your magnetization, okay. And now if you are going to start decreasing your magnetic field, it is not going to take this path again, rather it's gonna become something like this, okay. And when you reach to a certain negative magnetic field, you are going to have a zero magnetization. This negative magnetic field again is called your coercive magnetic field, okay. Similar to this concept of a coercive magnetic field, we define a term known as coercivity, okay. So your coercivity determines the amount of magnetic field that needs to be applied for your magnetism to become zero, okay. Just realize, even at zero magnetic field I do have a remnant magnetization, okay. This is known as your remnant magnetization or residual magnetization or retentive magnetization, okay. So corresponding to this term we have what is known as retentivity, okay. So it is the amount of magnetization retained or present when there is no magnetic field, okay. So this was your hysteresis loop as you would decrease your magnetic field. Now if you are going to again increase the magnetic field, you are going to trace out a new path which is going to be something like this, okay. So this is your hysteresis curve, similar to what we have already seen in dielectrics or ferroelectrics, okay. Just realize, we had earlier seen that my magnetic flux density is equal to mu 0 H plus M, okay. In a ferromagnet, this factor, magnetization, is more pronounced, okay. This factor basically determines your magnetic flux density, okay. So you can pretty well say that your B is almost equal to mu 0 into M, okay. So if you are going to trace a graph between your flux density and your magnetic field, then also you are going to get a same hysteresis loop, okay. Also, as it is visible from this graph, there is a complex relationship between your M and H, okay. So for a ferromagnetic material, your